Okay, let's do this question. Let A be a real 3 by 3 matrix and we are asked to find which of the following conditions does not imply that A is invertible. Okay, so you have choice A. Minus A is invertible. Okay, so let us first check these choices one by one. We have been given that negative A is invertible. So this means negative A inverse X's. Now this means negative A raised to the power of negative 1 is indeed equal to negative A raised to the power of negative 1. Okay, so this is always true. Now you have to understand there's a lot of difference between this and this. Over here we take the inverse for negative A, but over here we take the inverse and then we multiply by the negative sign. So apparently the left hand side is equal to the right hand side. Okay, now with that being said, let us go and check if indeed negative A being invertible has got any impact in deciding if A is invertible or not. Okay, with this, let us first get the definition of A being invertible. Let me write that. If A is invertible, then there exists some B such that A times B is equal to I. I is the identity matrix. Let me write this as 1. Okay, and from 1 let us write, so this equation 1 I'm going to write it as negative A raised to the power of 1 be equal to C for some C. Okay, right, so of course this C is element of R. Now we know from algebra A raised to the power of negative 1 is 1 over A, so I'm going to rewrite this as 1 over A with a negative sign is equal to C. Then I'm going to cross multiply. I'm going to write 1 is equal to C times of negative A. Then I'm going to rewrite this as negative C times A. Okay, now clearly this is actually going to be rewritten as A times of negative C being equal to I, because we are producing I here. This means since A times some C is equal to I, this would mean A is invertible. Okay, so that's the meaning of this, because by definition of invertible, if A is invertible, then there is exists some B such that A times B is producing I. So in this case also we are able to show that A times negative C is equal to I, subsequently giving us the all important deduction that A is invertible. So what is the point in showing you all this? It means that negative a being invertible means a is invertible. Okay, that's the exact meaning. So this statement is true. So we will move on to check the next statement. Now this is the second statement, B. It says that there exists a positive integer k such that determinant of a raised to the power of k is not equal to 0. Now the question is, does this imply a is invertible? Okay, so we need to check that. Now we are given that determinant of a raised to the power of k is not equal to 0. Okay, so I'm going to start like this. Since determinant of a raised to the power of k is not equal to 0, this means a raised to the power of k is invertible. Okay, now this directly means a is invertible. Now why do I say that? K is actually some positive integer. This has got no impact on deciding if ak, or I would say in deciding if a is going to be invertible or not, right? Just because I take k is equal to 3, there is no guarantee that k times, or I would say a times a is going to be invertible, right? There is no guarantee for this. So whether a being invertible or not invertible does not depend on the value of k, right? It depends only on the parent a. So if a raised to the power of k is invertible, then it means a is invertible. So this statement is also true. Okay, this is the statement number C. Let me write that down. There exists a positive integer k such that I negative a raised to the power of k is equal to 0, where I is a 3 by 3 identity matrix. Okay, so the requirement is, does this imply a is invertible? So that's the requirement we need to prove. Now what is that we are given? We are given that I negative a, you're watching, I negative a raised to the power of k is equal to 0. This means I negative a is nilpotent. So this means if I were to take I negative a is equal to some n, I have a is equal to I negative n. Now to show a is invertible, we need to show I negative n raised to the power of minus 1 excess. If I were able to show this, then this would mean that a is invertible. So that is our objective. So let us go and get that. Let me go to the next page. Now let me consider I negative n raised to the power of negative 1 before going to that statement. Now n is nilpotent, right? So this means n raised to the power of k is equal to 0. Let us consider the series expansion of I negative n raised to the power of negative 1. So I can write I negative n raised to the power of negative 1 to be as I positive n squared plus etc. n raised to the power of k negative 1 with n raised to the power of k being equal to 0. This I'm going to be multiplying both sides by I negative n. So you have I negative n raised to the power of negative 1 is equal to I negative n multiplied with 1 positive n squared plus etc. n raised to the power of k negative 1. This into I is going to be 1 positive n squared plus etc. n raised to the power of k negative 1. Negative n times this entire thing. So n positive n squared plus etc. n raised to the power of k, right? So you subtract these. So what do you get? N and n goes off, n squared and n squared goes off, n to the power of k negative 1 also gets cancelled, giving you 1 negative n raised to the power of k. On the left, what you got? I negative n times I negative n raised to the power of negative 1. But n raised to the power of k is equal to 0. This means is equal to 1. So the meaning of this is I negative n times I negative n raised to the power of negative 1 is equal to 1. This is actually identity, right? So this means I negative n as an inverse, right? This means I negative n is invertible. Okay, but what is I negative n? Write that. But I negative n is equal to a. This means a is invertible. Okay, so this choice C also implies that a is invertible. Now this is statement D. It says that the set of all vectors of the form AV where V is element of R3 is R3. Now what is the meaning of this? Can you tell me? It means the image produced by the linear transformation is all of R3. So in representation they are telling us image of A is equal to R3. So what is the meaning of this? This means A is surjective. Okay, so once A is surjective, the inevitable implication is A is invertible. Now you might be asking me how. So let me give you this important fact. For a square matrix, in this case the order of the matrix is 3 by 3. Okay, the following are equivalent. A is invertible. Determinant of A not equal to 0. A is full rank. The rank here is equal to 3. A is injective. That means 1 to 1. Number 5, A is surjective. 1 to. Number 6, AB, if it is equal to 0, implies that V is equal to 0 only. So that's the only solution that is existing. So if AB covers all of R3, then A is surjective, then this means A is invertible. Okay, so choice D, statement D is also true. True in the sense it implies A is invertible, but they do not want the true statements. They want to find the odd one out. That's exactly what we're going to do when we check E. Now this is the final statement. Now what they are saying here is there exists 3 linearly independent vectors v1, v2, v3 element of R3 such that a v I is not equal to 0 for every I. Okay, now what they're saying is if this condition holds good, the claim is A invertible, or I would say A is invertible. We need to find that out. So just because this is a solution I'm giving, given that v1, v2, v3 element of R3 and AV1 not equal to 0, AV2 not equal to 0, AV3 not equal to 0, does not guarantee AV1, AV2, AV3 are linearly independent. This means A is not invertible. Okay, you understand what I'm saying? So the idea is AV1, AV2, AV3. Of course, they are not equal to 0, but that does not mean that they are linearly independent. Okay? You catch my point? Just because they are not equal to 0, the condition does not guarantee AV1, AV2, AV3 are linearly independent. Okay, so this is all important word. Now the question is, I'm going to give you a small proof, or I would say a small illustration to show that just because v1, v2, v3 are vectors, non-zero vectors, and the application of A onto v1, v2, v3 are also non-zero, does not guarantee the linear independence of AV1, AV2, AV3, and this is required for showing that A is invertible, but apparently this will fail. So that's exactly going to be my illustration. Okay, so let me take this example, A being equal to 1, 0, 0, 0, 1, 0, 0, 0, 0, and the vectors v1 being 1, 0, 1, and v2 being 0, 1, 1, and v3 being 1, 1, 0. Now I'm going to perform this transformation, A multiplied with v1. This is going to be 1, 0, 0, which is nothing but I. A multiplied with v2. This is going to be 0, 1, 0, which is nothing but j. Okay, and AV3 is going to be, if I were to multiply A with v3, it's going to be 1, 1, 0, which is nothing but I vector plus j vector. So clearly we see that one vector, say for example if I were to take u1 vector as I vector and u2 vector as j vector and the u3 vector is I vector, that's exactly what we got, right, plus j vector, then in this case I can write u3 vector as a u1 vector plus u2 vector. So that means one vector is written as a linear combination of other two vectors. So this means statement E does not imply A is invertible. Okay, so this is the choice that you will have to circle it in.